Hello, multivariable calculus students. This is Mr. Johnson, and we're going to start chapter 11. This is section 11.1, which is on functions of several variables. And a little bit of this is going to be review from chapters 9 and 10, where we started to at least introduce the idea of the domain and range of a function of multiple variables. But we're kind of outside of the realm of vectors for the moment, and we're going to talk just about how we've been able to represent a value given multiple variables. So for example, if we think back on something as simple like the volume of a cylinder, the volume of a cylinder is pi r squared h, and we've always written it as v equals in the past, but we could write that as v as a function of r and h. In other words, the volume itself has two inputs to it, r and h, and the output is the volume. And so this is just one of obviously many examples of functions that we've utilized in the past that have actually made up of multiple variables. And so we're going to study this now in chapter 11, more so in the context of a Cartesian idea or a rectangular idea in terms of x, y, and z in space, rather than in the vector form. But we are going to combine the two as well. So in the chapter, we're going to look at the transition from single variable calculus to more of the multivariable calculus with regard to functions. And we're going to look at it in a very similar way that we've looked at AP calculus in the past. We're going to look at the four different elements of questioning, which is verbal, numeric, algebraic, and then visual. So the first example I have for you is really simple. It's just an algebraic example. We're going to have this plenty of times where we have to find a function value. And we've done this obviously in the past as well, but we're going to look at, okay, what if we have a function made up of two inputs and we want to know the function value at, let's say, the x value of 2 and the y value of 1. We simply just do substitution of those values into the function formula and we get the output. So that would be representative of the z value. That would be on the z-axis. So for example, we're going to start to study a slope of a surface at a particular point. So we need to know the x value, the y value, the input, and that will give us then the z value, and that's the point at which we'll find a tangent plane, for example, or maybe a linear approximation or something like that. The next example is a verbal and a numeric example, and so we can relate to this in the winter here. It says that certain regions have severe weather, and the wind chill index is often used to describe the apparent severity of the cold. This index W is subjective temperature that depends on the actual temperature T and the wind speed V. So W is a function of T and V, and we can write it as kind of similar to that cylinder problem. We can write it as W equal to F of TV. So the input is capital T and the input is V, and we have an output then of W. So the table below shows values of W compiled by the National Weather Service. And so what we're going to look at here for our particular problem is if the temperature is -5 degrees Celsius and the wind speed is 50 kilometers per hour, we want to calculate the wind chill simply by looking at where we are on the table. So we're looking at -5 degrees Celsius, we're looking at 50 kilometers per hour, and so we find that the wind chill is -15. So again, we have W of -5 and 50, and we in turn get a wind chill of -50. And so again, and that would be degrees Celsius, and we are able to look at this function of multiple variables just based on the table here and a verbal explanation. Okay, let's go on to the next page. All right, so for our next page, we're going to look at the domain and range. And I have a series of graphs to show you just as a visual. I think that's really helpful. But the first thing is we're going to analyze the domain and range by looking at the problem and using our knowledge of these types of functions. So for example, this first one, we know that with the square root function of a radical, we have the inside which needs to be positive. So in other words, we have 9 minus x squared minus y squared must be equal to greater than or equal to 0, and we can rearrange this and write it as x squared plus y squared is less than or equal to 9. And that has a little bit more meaning to us because we do know that that's a circle centered at the origin with radius of 3. But we can describe the domain in this case as having that restriction, but more importantly, all the xy in 2 dimension, so in the 2 dimensions of the xy plane, are going to be okay as long as they are satisfying this particular inequality. So that's our domain here. Now, as a graph, we have on the xy plane a nice easy representation of this restriction. So we have a circle which has a solid outside, a radius of 3, and the inside is all filled in. So, again, let's try to put this into a visual context. If we were looking down on this surface from, above on the z-axis, let's say we're way up on the z-axis and we're looking down like we were hovering above it, this is the shadow or the shaded area that would exist of this particular surface. Now, we don't know exactly what the surface looks like right now with regard to as it rises up at us as we look down on it. We don't know exactly what the shape is yet. We don't know how far down it goes into the xy plane, or maybe it doesn't even go past the xy plane. But what we do know is that if we were to take the three-dimensional surface and we were to simplify it to a certain extent, kind of take away the z-axis in general and just look down on it, this is the picture that we would see. And I'm going to show you that in just a moment because I have a computer-generated form of this, and I think it's really helpful to think about it that way. Okay, let's go ahead and analyze the range of this. Now, we know, algebraically here, and by the way, anytime we have the function written like this, we could think of it as z equals rather than g of xy. And if that's helpful, then go ahead and even make that substitution. So what I was going to show you was that z is equal to the square root of 9 minus x squared minus y squared. And this is one that, based on our knowledge of chapter 9 and 10, we may be able to get to right away. But if we were to square both sides and just rearrange this, I think you'll see really quickly that this is a surface that we should know about because we studied it a lot. This is a sphere with a radius of 3. Now, based on the original statement of the equation, z can only be greater than or equal to 0. So therefore, this is the top hemisphere of a sphere centered at 0, 0, 0 with a radius of 3. So that gives us a really distinct picture of what's going on here. But the question is, what is the range? Well, so the range, if we were to sort of just think through, okay, we can see this sort of top portion of this sphere. The z value is anywhere from 0 to 3, including both 0 and 3. Okay, so I have a little bit, let's see, I have a little picture here to show you all. So this is the surface, and the blue axes that you can see sort of as a shadow right here, that's the z-axis. You can see the y-axis, you can see the x-axis, you can see the spherical shape, the top hemisphere of this particular surface. I wanted to also show you the domain. So this isn't quite perfect, but pretend like we're sitting right up here on the z-axis looking straight down. You can see that circular shape right there. You can see that it's a circle centered at the origin with a radius of 3. And again, I can't quite do it perfectly, but you can get a good sense that if you were to just take away the three-dimensional aspect of this and you were just to look straight down on it, you can see that there's a nice circular shadow that we had graphed for the domain. And then I also wanted to show you the range. So this is sort of a side profile of this. You can see that it sits right along the xy plane right here. It just sits there. So the minimum is 0. The maximum you can see is 3, and you can see that hemisphere form. These little lines that are in here, or curves I should say, those are traces, and we're going to be talking about that in the second half of this particular section. Those traces allow us to get a sense of what the surface looks like. All right, let's go on to the next example. So we're looking at example 4. Same kind of thing. We're just going to look at a new set here. So we're looking at the domain first. And with this domain, we know that with a natural logarithm, the argument, which is 9 minus x squared minus 9y squared, must be greater than 0. And we just know that based on the properties of the natural logarithm. So if we were to rearrange this, we would have x squared plus 9y squared is less than 0, is less than 9. And a little bit more formally, if we were to divide by 9, we would get the inequality that represented an ellipse. So this is going to be our domain, and I will graph that here as well. So we're looking at all points xy in the xy plane such that that particular inequality holds true. Okay, so if you were to graph this ellipse, keep in mind that the outside of it is not included in the particular values that work here, but we have on the x-axis a maximum of 3 and a minimum of -3, and on the y we have a minimum of -1 and a max of 1. So we have this sort of dashed outline here. Pretend like that's perfect, and then we have any value inside that is part of the domain. So again, same kind of thing. If you're staring at this from above along the z-axis where you eliminate the three-dimensional aspect of the surface, this is the shadow that you would see, and I have a graph to show you that. All right, let's think about the range. Okay, this one's a little bit more complex because based on the algebraic approach, we don't quite have the whole idea of a like we did with the sphere in mind. Keep in mind that this graph could be written as z equals. Okay, I know it's h of xy, but you could write it as z equals. And so when you're thinking about what z could be, what values could exist on the z-axis, we have to be a little bit more creative with this. Okay, let's think about the maximum first. That might be easier. Now, since x squared and y squared are being taken away by subtraction, the maximum of this argument is 9. And that's going to be when, I'll try to squeeze this in, when x and y are equal to 0, 0. Because again, they're both being taken away. And so the maximum value there will be when they're both 0, otherwise you'd be taking something away. So the maximum is going to be actually the natural log of 9. So I'll write that down a little bit. The minimum's a little bit more difficult, I think, because when you think of, for example, let's say we take the limit as x goes to 0 from the right of the natural log of x. So I'm kind of reverting back to single variable calculus for a minute. So when you think of the natural log of x, and you think of the graph of the natural log of x, as x goes to 0, that graph is going to approach negative infinity. The graph does something like this, where you have natural log of x like this. So as you approach 0 from the right side, your graph is going to negative infinity. So the question then really becomes, as we're looking at the argument, so again, we're now in multivariable form. So the argument that we just analyzed was the natural log of x. So x was the argument. But in this case, the argument is 9 minus x squared minus 9y squared. So the question is, as that goes to 0 from the right, so collectively as it goes to 0 from the right side, z, or let's just make it h of xy, is going to negative infinity. So we're changing this into, our next section is going to be on limits of multiple variable functions. But in this case, I'm just kind of introducing that idea. So as the argument goes to 0 from the right side, the function is going to go to negative infinity. So in other words, for our range, the minimum is negative infinity. It's going to just keep on going down forever. And this is for h of x, y, or z. And the maximum is the natural log of 9. Okay, let's take a look at our visuals over here. So here's the graph, and this graph does end at about -5. So this would continue down here forever, but in the particular app that I'm using here, it does end at -5. But you can see that the overall shape, maybe it makes some sense based on what we were analyzing, maybe what you were thinking in your head. But if you were to look, here's the view from above. So we're sitting here at positive z, somewhere up in positive z. And I know it's not perfect, but you can see this elliptical shape that just formed on the xy plane, from 3 to -3 and -1 to 1. And again, that's going to be the kind of the shadow of what's possible with x and y. Keep in mind that it's not a perfect elliptical shape on the xy plane, because that's not where this graph ends. This graph ends at -infinity, so it's going to be kind of continuing to go down forever there. And then here's a look at the range. I know that it was pretty obvious from the previous one as well, but this is sort of a side view of it. So again, the maximum is here, and at ln of 9, and then it goes down forever. And again, this just stops at -5, I think, on the z-axis, but it just keeps on going down forever. All right, let's continue. A couple more examples here. So we have example 5. Another function. This one's a little bit faster, actually. So the only thing that messes up something like this would be when the denominator is 0. So in other words, we cannot have, we cannot have. So y is not equal to -x. That would be our domain. So in other words, we have all points xy in the xy plane such that that equation holds true. So anything except the fact that x and y cannot equal the opposite of each other. So we have a graph that looks something like this. It's a little bit more unique, but kind of cool when I show you the picture of it. So you have this dashed line, y equals -x, excuse me. Every other point other than the points on that line are okay in this particular domain. So you can imagine that this is going to look like some sort of three-dimensional asymptote. And so I'll show you that in just a minute here. Okay, let's talk about the range. So we're going to look at a similar approach here. Think of it this way: as x plus y, as the denominator approaches 0 from the right side. So as the denominator gets really small on the positive side of 0, the function is going to go closer and closer to infinity, 1 divided by a very small positive number. As x plus y grows closer to 0 from the left, then your function is going to grow closer and closer, or go closer and closer to -infinity. So in other words, when you divide by a very small negative number, your function is going to be closer and closer to -infinity. So our particular range will be all values except, there's no way for, actually I'll write it this way. So the range is anything except f of xy cannot equal 0. There's nothing that I could put in for x and y that would cause the function to be 0. So we will have these kind of three-dimensional asymptotes that are going to form. I'll show you that over here. So we have a look from above, from the z-axis, and you can see this, this line, y equals -x form, and you can see that anything beyond that line is part of the domain, but that line there causes an issue with this particular function. And here's a nice look from the side. You can see that this particular function, as you approach, as x plus y approaches 0 from the right side, you can see this function goes to infinity, versus from the left side of 0 goes to -infinity. So I think that's a really nice picture of this one. Again, you can see these curves that are forming, those traces, and that's what we'll be talking about here in just a minute. All right, let's try one last example. This one I cannot graph because this is in 4 dimensions. This is the function f of x, y, z. So there are 3 inputs. X, y, and z are all input independent values, and the function f is the dependent value. So we can't visualize it, can't graph it, but we do know properties of these functions. We know that the natural log has a property that the argument z minus y has to be greater than 0. You could write that as z is greater than y if you wanted to. It doesn't really matter too much with regard to that. But that's one statement, and then you can look over here, x and y, those are anything regarding at least this multiplication, and the input of sign can be anything as well. So the only real restriction is that z has to be greater than y. So for the domain, we have all values x, y, and z in 3 dimensions now, so in space. So any x, y, and z in space, so as long as the z value is greater than y. And in terms of the range, we're really not able to discuss that because, again, this is not something that we can visualize in space because it's four dimensions. All right, the next video we will talk about level curves and traces. Thank you.